Alright, so we're going to finish our discussion on waves up with talking about one-dimensional waves. And so here I've just kind of drawn a rod or a bar. And just to make things a little bit easier, let's say that we don't have any restrictions on our displacement in the x direction. That's the u displacement. But our other displacement components, v and w, are equal to 0. And this u displacement is only a function of x. So I have drawn up on the top what might represent, just think of it like a rod. Think of it as an infinite medium. Maybe our coordinate system starts here. And on this side we have the plus x direction. And on this side we have the minus x direction. If we do something to create a disturbance at this point, the waves will go either way. Our wave equation will look something like this. The second partial derivative of u with respect to time is equal to some c1 constant squared times the second partial derivative of u with respect to x. Now, in this case, the u is not a u sub I, it is only the displacement in the x direction. And for an infinite medium, then we can find the solution to this as some function of x plus c1t plus another function, we'll call it f1, of x minus c1t, which gives the propagation of the wave in the plus x and the minus x direction effectively. Again, c1 is our wave speed. And for this, there's good discussions in PDE's books, and I'll leave that to you to look a little bit more. The functions f and f1 define the shape of the wave. Whatever it looks like. And maybe it's kind of a nice, smoothly changing function from one end of this thing to the other. Maybe it looks like a hump of a sine wave. And this disturbance, this sine wave thing, it travels down the x-axis, and maybe after a few seconds, or fractions of a second, this hump has moved to this new position with the dashed line. This movement can be determined by the velocity, the speed, and the time. So this would be c1 times delta t, which would give the amount of movement, amount of displacement of that wave. So think of this hump traveling down this page, and drawing it as a hump, some kind of function like that, you have to be a little bit careful. It's not really displacing in the vertical direction. It's just trying to show this compressive wave of material that's at this time. It's traveling down this way, and now it's over here. And within that zone is this certain amount of compression, if you will. That's this hump from here to here, and now it has just moved down from here to here, where this hump just kind of gives us an idea of the compression that material is undergoing as it travels down the x direction. Alright, so let's write down the distance traveled is the wave speed times the amount of time. Alright, so let's investigate this wave speed just a little bit. Remember we said previously that our wave speed c1 was the square root of lambda plus 2g over rho. Now, those are in terms of the Lemay coefficients, and it may be more convenient to write these in terms of Poisson's ratio and the modulus of elasticity for a material. So if we do that, maybe you're more familiar with those terms. Then the c1 would be the square root of E times 1 minus nu divided by 1 plus nu, 1 minus 2 nu, and then we have the density of the material. Let's plug in some numbers just to kind of get an idea of what wave speeds and metals might be. We know that the modulus of elasticity of steel, for example, is 210 gigapascals. Poisson's ratio is around 0.3 in most of our metals. And in consistent units, our density is about 7,900 kilograms per cubic meter of material. Right, so let's put some of these numbers in. We've got 210 giga, that's 10 to the 9th, newtons per square meter. Now, Poisson's ratio is unitless. And then we have in kilograms per cubic meter, 7,900. And all of that's under the square root sign. Let me get my calculator out. Let's just see what we get for that. I'm going to pause the video for a second. Before I go too far, one other thing I need to do. This is a mass density, and I need to multiply that by gravity. So I need to take 9.81 meters per second squared down here. Okay, now I'll get my calculator out. Okay, made a mistake here. Need to erase a term. Actually, don't need to multiply this by gravity. This is just the mass density, so I'm going to get rid of that 9.81. Now we have to be a little bit careful in this when we do this in next step. So let's write all of our numbers down again. We have 210 times 10 to the 9th Newton per square meter. Now you may remember a Newton is a kilogram meter per second squared. We're going to divide that by meter squared. We got the 1 minus 0.3, and then we have 1 plus 0.3. We got 1 minus 2 times 0.3. Then we have 7,900 kilogram per cubic meter. And all of this is under the radical. The kilogram will cancel out. We have then the meter terms that we have to worry about. So this is like a, one of these will cancel out. This is like a meters on the bottom. This is a meters cubed, 1 over meters cubed that flips back up to the top. So we have a meter cubed divided by a meter term, which gives us meters squared per second squared. Okay, so when we take the square root, we end up with units of meters per second. And when I used my numbers, I got 5.98 times 10 to the 3. Okay. So that should be the wave speed of a longitudinal wave in steel. Now, you can look this up on the internet as well. I found a website, let me bring it over here, that lists some longitudinal wave speeds. And let's see, here's 1020 steel, 5,890 meters per second. Okay, and that's right in there with what I got. Now I made some assumptions about our modulus of elasticity and our density that might be a little off, and Poisson's ratio. So the point though is that it's right in there with what we would expect for a longitudinal wave speed in steel. Alright, now if we want, we can do kind of a similar analysis for transverse waves. Let's save this page. So in this case, our displacements u and w are 0. We only have displacements that go in the y direction, in which case our wave equation in one dimension reduces down to second partial of v with respect to time twice is equal to another constant c2 squared, second partial of v with respect to x. So it's still traveling down the x direction, it's just the displacements are perpendicular to the direction of travel. We saw that our wave speed for c2 is the square root of g divided by rho. We can express this in terms of our previous wave speed for the same material, the same density, as 1 minus 2 nu over 2 times 1 minus nu. And if Poisson's ratio is equal to 0.3, then we can find that C2 is equal to 0.535 times C1. And for Poisson's ratio is equal to 0.25, maybe for aluminum, then we can show that C2 is equal to C1 divided by the square root of 3. So that shows that the transverse waves, the distortional waves, are traveling more slowly than the dilatational waves. Now, I do want to mention that a lot of this discussion has been pulled from several different sources. Our book that we use in our elasticity class, as well as sources that I found in other books, and including Timoshenko and Goodyear's theory of elasticity. Alright, so I think that pretty much does it for us here. Waves are fairly important, fairly interesting. They have lots of different applications. I am not a wave expert by any means, but I wanted to show you some of this information so that you can jump into the wave equation for stresses and solids, particularly stress waves and solids, and kind of get an idea of what's going on. The last thing I do want to mention is there is something called the explicit dynamics finite element approach. You may hear me from time to time talk about abacus explicit. It's used for high rate deformation, metal forming type problems, ballistic impact, and so forth. The main solution procedure that it uses for this dynamic event is the wave equation for stresses and solids. This is opposed to more traditional static, quasi-static finite element technique, which inverts a stiffness matrix in order to find stresses and displacements. Abacus explicit solves the wave equation through for your stresses and displacements in your material. So if you get a chance, I would suggest that you take a look at the theory manual for Abacus Explicit, and it'll give you a little bit more of a background on how that all works and fits together with what we've just talked about.